Imagine you're standing in a silent room. No movement, no sound, no light, just stillness. Yet all around you, hidden beneath the surface of materials, a powerful sea is in motion, an ocean not of water, but of electrons. And the number of electrons swimming in this invisible sea, that's what powers your lights, your phone, your computer, even your brain. Today, we explore the density of electrons in the conduction band, a concept that bridges quantum physics, engineering, and the entire digital age. Chapter 1: Bands that change the world. In the early 1900s, scientists couldn't explain why copper conducts electricity so well, why glass doesn't, and why silicon is somewhere in between. The answers came with quantum mechanics. In solids, electrons don't behave like isolated particles. Instead, they exist in energy bands, allowed zones, separated by forbidden gaps. In metals, the bands overlap. In insulators, the gap is too wide. And in semiconductors, like silicon, the gap is small, just enough for electrons to jump if they're given some energy. That jump, from the valence band to the conduction band, is where the story of electron density begins. Chapter 2: What is electron density? When we talk about the electron density in the conduction band, we mean this: how many electrons are free to move per cubic centimeter of material. But this isn't about counting marbles. Electrons follow quantum rules. They don't fill up energy levels randomly. They follow the Fermi-Dirac distribution, a probability law that tells us how likely it is for an electron to occupy a specific energy level at a given temperature. The total number of conduction electrons, which we call N, is calculated by multiplying two functions. First, the density of available states, and second, the probability that each state is occupied. Then we integrate. That means we sum across all energies starting from the conduction band edge and going upwards. In plain language, the electron density N is the sum from the conduction band edge to infinity of the number of available states at each energy level, multiplied by the chance that each level is filled. Let's break that down. Chapter 3: The equations made simple. Let's start with the density of states, which tells us how many quantum states are available at a given energy. In three-dimensional space, it increases with energy and is given by a formula that sounds complicated, but can be spoken like this: the density of states is proportional to the square root of the difference between the energy level and the conduction band edge. It's also multiplied by constants, involving the effective mass of the electron, pi, and Planck's constant. Next, the Fermi-Dirac distribution. The probability that a state at energy E is occupied is 1 divided by 1 plus the exponential of the energy minus the Fermi energy, all over Boltzmann's constant times temperature, at room temperature. And for most semiconductors, this equation simplifies. So the final result, the conduction electron density, becomes capital N sub C, which is a constant for the material, multiplied by the exponential of the negative difference between the conduction band edge and the Fermi energy, divided by Boltzmann's constant times temperature. This is the formula that engineers use daily. It allows them to predict how many electrons will be in the conduction band at a given temperature. Now, what exactly is N sub C? It's called the effective density of states in the conduction band, and it's given by 2 times the quantity, 2 pi times the electron's effective mass, times Boltzmann's constant, times temperature, divided by Planck's constant squared. The whole thing raised to the 3/2 power. This value changes with temperature and material type, but once known, it helps us estimate how conductive a material will be. Chapter 4: Doping, turning the knob. In pure semiconductors, Like clean silicon, electron density is low. That's not great for building circuits. So what do? We dope it by adding phosphorus atoms. Each one gives the material an extra electron. These extra electrons push the Fermi level closer to the conduction band. And here's the magic. The closer the Fermi level gets to the conduction band, the smaller the energy gap in our exponential formula, and the higher the electron density. In N-type doping, we add donor atoms that give away electrons. In P-type doping, we add acceptor atoms like boron that create holes by pulling electrons from the valence band. This process lets engineers tune the number of electrons available. Essentially, it's like turning the volume knob of conductivity. Chapter 5. Why this matters to your life. This might sound theoretical, but it's incredibly practical. Every transistor in your computer uses this principle. By applying voltage, engineers bend the energy bands, shift the Fermi level, and control how many electrons enter the conduction band. In solar panels, sunlight energizes electrons, pushing them from the valence band into the conduction band, creating electricity. In LEDs, electrons fall from the conduction band back to the valence band, releasing energy as light. The band gap determines the color of the light. Even in medical devices, controlling electron density lets us design materials that safely interact with the human body. Chapter 6. The cutting edge. The frontier today lies in new materials. With graphene, transition metal, dichalcogenides, and 2D semiconductors, we're creating materials with exotic band structures. In quantum wells and superlattices, we confine electrons in thin layers, forcing them into specific energy bands with customized densities. And in quantum computing, quantum dots, tiny particles that trap single electrons, depend entirely on precise control of electron density in energy bands. Chapter 7. Beyond Earth. Even in space, this matters. Satellites exposed to cosmic rays see changes in electron density, which affects their circuits. Future habitats on the Moon and Mars will need materials whose conduction properties remain stable across extreme temperature swings, from -150 to +100 degrees Celsius. In these environments, knowing how electron density shifts with temperature isn't optional, it's survival. Epilogue. The sea beneath the circuit. You'll never see an electron jump bands. You won't hear it. But every time you touch your phone, ask a question, or take a photo, millions of electrons are flowing through the conduction band. Their number is controlled by physics, by temperature, by material, and most importantly, by human design. Electron density in the conduction band isn't just theory. It's the foundation of the digital world, a silent sea we've learned to command. And now that you know how it works, you're riding the wave too. Thanks for watching BroadScience. If this video sparked your curiosity, like and subscribe for more stories where quantum mechanics meets real life.